Okay, we're going to continue in this video talking about experimental uncertainties. And in particular, we're going to learn about something called the propagation of uncertainty. So what does that mean? So let's consider a square, and we get out a ruler and we measure the lengths of the sides of the square. And then we want to determine what the area of the square is. And so we want to be able to calculate what the area of the square is. Now, if you measure each side to be 10 centimeters, then obviously the area is going to be 100 centimeters squared. I mean, I say that's obvious. I hope it is. I've got the area is going to be the length times the width. So that's going to be 10 centimeters times 10 centimeters. And so that's going to give me 100 centimeters squared because I have centimeters times centimeters. Now, here's the problem with that. If I go into the lab and I measure something, I'm not going to measure it to be 10 centimeters. I'm going to measure it using an instrument that has a built-in uncertainty. And so it's going to be 10 centimeters plus or minus some amount. Now, I've suggested here are 10 plus or minus 1 centimeter. That, of course, would be a gigantic uncertainty for that kind of a measurement. But this is just to illustrate the idea. So let's say I've got this side, I've measured it as 10 centimeters plus or minus 1 centimeter, and the same for the other side. What does that mean? That means this value could actually be as low as 9, and this value could actually be as low as 9, or each of them could be as high as 11. So we would say that that area is 100 centimeters squared, but it could be as low as 9 times 9. That would be 81 centimeters squared. Or we could say that each of these is as possibly as high as 11, and so that would be 11 times 11, or 121 centimeters squared. And so we could say 100 centimeters squared plus or minus, the amount of that range. And so that is the basic idea that when I have measurements that have a built-in uncertainty and I multiply them together, or I add them together, or I subtract them, or I take one to the exponent of another, that uncertainty is going to increase or decrease depending on what goes on. And we want to be able to know what happens to the uncertainty of the total if I do mathematical operations on measurements that themselves have built-in uncertainty. So just to recap, in our previous example, we calculated a quantity, in that case it was the area, which is a mathematical function of the quantities that had been measured with their uncertainties. In other words, the length and the width. We had measured the length plus or minus its uncertainty and the width plus or minus its uncertainty, and then we multiplied those together to get the area, length times width. Anytime you do a calculation involving variables whose values have an uncertainty, that is, they have a plus or minus part, that uncertainty must be, quote unquote, propagated through the calculations. And so that's what we're going to talk about doing in this video. So let's assume that we have a series of measurements whose values are A. A is the result of the first measurement, B is the result of the second measure. We can have A, B, C, all the way through X, Y, Z. And then each of those variables has a corresponding uncertainty, delta A, delta B, etc. So my measurement for the first item would be A plus or minus delta A. My second one would be B plus or minus delta B, and so on. Now let's assume that there's some calculated quantity Q, which comes from adding and or subtracting those values. That is, Q is equal to A plus B plus C plus D, or minus G, whatever, plus or minus these other variables. And so if I have a bunch of things that I've measured, and each of them has a plus or minus delta whatever, how do I determine the uncertainty of Q? So I would have Q is equal to some Q plus delta Q. How can I figure out what the delta Q is if I know the delta A, the delta B, etc.? Well, it turns out there's a formula, and it looks kind of similar to the Pythagorean theorem, but what it really is you simply say, okay, I'm going to take the uncertainty of A and square it. I'm going to take the uncertainty of B and square it. And for however many measurements I have, I'm going to take each of their uncertainties and square them. And then I'm going to add all those values up. And then finally, I'll take the square root of that to get my delta Q. And so I have my Q, which is A plus B plus whatever, and then my delta Q is all of that. And then I can give you my answer, which is going to be some Q plus or minus some delta Q. And remember, these are actually going to be numbers. So we'll have, 17 plus or minus 0.07 or whatever it is, And so if the formula that you're plugging things into is simply an addition or a subtraction of the things you've measured, the uncertainty is very straightforward to calculate. Now, what if you're multiplying things together? And of course, multiplication and division are essentially the same thing. You're either multiplying by A or you're multiplying by 1 over A in order to divide. And so we could have some quantity Q that is the product or the division of things that we have measured. So I've got A times B times C times whatever divided by, W times X times Y times Z, whatever you have. So what would be the uncertainty in Q? Well, what we would find is that delta Q divided by Q, and of course Q is what you get when you do all of these multiplications and divisions. So if I take delta Q and divide it by Q, that's going to be equal to delta A over A squared, where A is the measurement and delta A is the uncertainty of A. So I've got my A here, but I've measured A, and so I've really got an A plus or minus delta A. I've got a B plus or minus delta B. And so I'm taking all those delta A's, delta B's, delta whatevers, and I'm dividing them by the term that they go with, then I'm squaring them, I'm adding them all up, and then I'm taking my square root. And so I could write this another way. I could say that delta Q is equal to Q magnitude times that square root of all that stuff. And then I could say I have my Q, which is, of course, just simply multiplying and dividing all these things together. That's how I get my Q. And then I would say I have Q plus or minus delta Q, where my delta Q is calculated using this formula. Are you starting to get the sense that calculating uncertainties can be a little complicated? It can. Let's see a bit more. Oh wait, here's a good one because it's actually not that complicated. Some formulas have exact numbers. For example, later on, we're going to learn the formula for something called kinetic energy. I've got kinetic energy, and the formula for kinetic energy is 1/2 times the mass times the velocity squared. You may have seen that before if you took chemistry or if you took physics in high school. It doesn't matter if that formula means anything to you or not. You just need to know there's a formula in physics that has this form. 1/2 times the mass times the velocity squared. Now here's the thing. That 1/2, that is exactly 1/2. It's not 1/2 plus or minus some stuff. It's just 1/2. That's in the formula. And so anytime you have a quantity that's measured by some exact number like that, and so X is what I've measured, and A is my exact measurement, and so Q is equal to, 1/3 X, or whatever it is, that exact number. To calculate my delta Q, I just multiply out like this. And so this would be my exact number times my delta X. So I've got my X that I've measured has got X plus or minus some delta X, and so my delta Q is going to be A times delta X. And I could write out Q plus or minus delta Q. Now, what about if you have a formula that has exponents? So here is Q, and it's equal to some X to the M power times Y to the N power, etc. And what we find is that, so my X is going to be some X plus or minus delta X. My Y is going to be some Y plus or minus delta Y. These are things that I've measured. I'm multiplying these together as exponents to get my Q. How do I determine what my delta Q is? Well, my delta Q over Q, again, I can bring my Q over to the other side if I want to just figure out what delta Q is. Look at this. I've got X to the M power. Here I've got M times delta X over X. When M is equal to 1, in the previous slide I had X times Y times Z times blah, blah, blah. All of these exponents were 1. But if I've got like x squared or x to the fifth or whatever it is, that number needs to be out front. And so here I have m delta x over x all squared, n delta y over y all squared, and I just keep repeating that for as many measurements as I have, and then I add them all up, and I take the square root. And again, that lets me calculate my delta q, and I can write down q plus or minus delta q. Now, obviously, you don't want to have to figure out this for every possible function. What if you have a formula that involves a sine or a cosine, or maybe it involves a natural logarithm, or a base 10 logarithm, or some other function? What can you do? Well, there's actually a way to do it. And the formula, so I've got my q here, and q is some function of these variables that I'm measuring. And it might be the sine of w minus the log of x. You know, it doesn't matter. It's just some weird function. And I want to know what my delta q is. Well, this says, so my q is a function of w, x, y, z, etc. I'm going to take the partial derivative of q with respect to w times the increment dw, square it. Then I'm going to take the partial derivative of q with respect to x with the increment dx, square that. I'm going to repeat that pattern for as many measurements as I have. I'm going to add up all of those squares, take the square root, and that'll give me my delta q. Now, if you're looking at this formula going, what the heck is a partial derivative? I've never heard of that before. Don't worry, you will. You'll learn that in Cal 3 or Cal 4 if you haven't gotten to it yet. I'm not going to expect you to know this formula or even to use this formula. I just want you to know that there's a formula. There's a way that we can calculate the delta q. So I've got some formula, and it says if I want to calculate q, I apply this function, and these are things that I've measured to plug into my formula. Each of these, the w is a plus or minus delta w, the x is a plus or minus delta x. How do I determine my delta q? I have a formula that will let me do it, even if I've got some bizarro land function up here that I'm using to plug my measurements into. And as you can see, calculating uncertainty is serious business. Now, here's something that is maybe worth thinking about. If I'm machining parts that are going to go into a nuclear reactor, I might want to be very, very careful about measuring my uncertainties and propagating them appropriately so that I know what the uncertainties that I'm dealing with in my design of a nuclear reactor that could, melt down and wipe out a city or something like that. So taking care of uncertainties is serious business. But if I'm building a table for my lab, maybe I don't care so much if I am exactly on where my uncertainties are. So my point is that, you're not always going to have to use all these formulas. In fact, more often than not, you don't even have to use these formulas that I've showed you. The reason that I showed you them is I want you to be aware that they exist. Later on, you'll actually learn how to use these formulas in some of your later classes when you're actually involved in measuring things or building things or designing things. But for everyday purposes, if you're just going into a lab and you're making measurements, you don't have to do all of this. You don't have to calculate the standard deviation of the mean of a set of 50 measurements, and you don't have to do all of this craziness. There are ways in lab that we can estimate the uncertainties we have, and there are ways that we can do calculations that we know what the uncertainty of our calculations are going to be. I've already showed you one of the ways that we can do that, and it's sometimes I've seen it called the crank 3 times method. So basically what you do is you have all your measurements and all their uncertainties, and you plug them into your formulas. And so you have to do it with the lowest possible value for each measurement, and then you do it with the biggest possible value for each measurement, and then you do it with the measurement itself, what your best average of your measurements are or whatever, and that's the crank 3 times. And so that gives you the upper bound and the lower bound, and that lets you come up with your area. And you would say your area is 100 centimeters squared, plus or minus the range between 81 and 121. And that's a perfectly good way of estimating your uncertainties. And it can be a useful trick if you need to do that. But there's also another way that we can estimate our uncertainties, and we can propagate our uncertainties naturally, and that's using what are called significant figures. Now, if you had chemistry, you already learned about significant figures. Maybe you had physics or chemistry in high school. You've already seen this before. That's what significant figures do. Significant figures basically, they keep track of your uncertainties for you, and they let you carry them through and propagate them through your calculations. Now, here's the dirty secret. Significant figures are a way of estimating the uncertainties. I've given you a hint that actually determining the real uncertainties can be complicated. But if you don't need to know exactly what your uncertainties are, and you just need kind of to understand, I'm making a measurement and my uncertainty is going to be within this range, significant figures are a powerful tool for estimating those uncertainties. Now, most of you already know how to use significant figures. So I'm going to put up a video on how to use significant figures, but it's going to be optional. I'm going to let you decide whether you need the review or not. If you already know how to use significant figures, then you can decide to opt out of watching that video. But if you're like, I'm not sure I remember exactly how to do it, then please watch the video, because I am going to expect you to know how to use them.